capable of generating sufficient thrust to take off with external power. Biologists have recently quantified the complex nonlinear temporal phenomena that give insects their outstanding capabilities. Periodic wing motions consisting of a large stroke and pronation and supination about an axis parallel to the span-wise direction are characteristic of most hovering dipteran insects. Previous micro-robot designs have attempted to concisely control each wing trajectory in these two dimensions. The MAV described here has 3 degrees of freedom, only one of which is actuated. Here, a central power actuator drives the wing with as large a stroke as possible, and passive dynamics allow the wing to rotate using flexural elements with joint stops to avoid over-rotation. There are 4 primary components to the mechanical system: the actuator, or flight muscle, transmission, or thorax, airframe, or exoskeleton, and the wings. Each is constructed using a mesoscale manufacturing paradigm called smart composite microstructures. This entails the use of laminated, laser micromachined materials stacked to achieve a desired compliance profile. This complated method is inexpensive, conceptually simple, and fast. For example, all the components of the fly can be created in less than 1 week. Additionally, the resulting structures perform favorably when compared to alternative devices. Flexure joints have almost no loss, ultra-high modulus links have higher stiffness to weight than any other material, and the piezoelectric actuators have similar power density to the best DC motors at any scale. After integration, the fly is fixed to guide wires that restrict the motion so that the fly can only move vertically. The wings are then driven open loop to achieve a large angular displacement. This is done at resonance to further amplify the wing motion. The wings exhibit a trajectory nearly identical to biological counterparts.
Așa. Și am ajuns la subiectele care vreau să le mai punctez mai interesante. Ideea de complexitate, colaborare și autoasamblare. Au apărut deja foarte multe direcții de cercetare în zona atât a colaborării, în care suntem și noi interesați, dar și în zona autoasamblării. Și sunt variante diverse, unele vor să devină molecule într-un lichid care se autoasamblează, deocamdată sunt la o scară mai mare. Conceptul de swarm sau ROI, traducere, Swarm Robotics presupune o populație relativ mare de indivizi relativ simpli care de obicei nu sunt diferențiați între ei. În unele situații, dacă ne gândim la roiurile de albine, de furnici, există o diferențiere pe câteva categorii de funcționalitate și care împreună colaborează într-un mod de colaborare locală, fără a exista un sistem central care să supervizeze toate miile de furnici, de albine și așa mai departe, și care creează valoare adăugată la nivelul sistemului. Dintre toate cele pe care le-am văzut, aș vrea să ne uităm măcar la aceasta, care mi se pare inedită prin faptul că a combinat 2 specii sau chiar 3 specii de roboți relativ diferiți sau foarte diferiți.
A recent trend in robotics is to get lots of robots working together. But parallel operation is not always enough. Some tasks are just too difficult for the robots to solve on their own. So-called self-assembling robots can combine forces by connecting to each other in a broad range of morphologies. But it's hard for the robots to know when to use different morphologies because of their limited local sensing range. The solution? Flying robots. Flying robots can analyze the environment to see what task needs to be solved, what morphology is most appropriate to solve that task, and which robots are best placed to form the morphology. However, it is non-trivial for the flying robot to communicate with specific robots on the ground. The problem is that the robots have very different views of the world, which makes it difficult for them to agree on a common frame of reference. We have developed a method that allows robots to select their communication partners without relying on any kind of global coordinate system. We refer to our method as spatially targeted communication. Let's say a flying robot wants to communicate with a specific robot on the ground. This one, for instance. To start the selection process, the flying robot illuminates its red LEDs. To join the selection process, the robots on the ground light up in blue. In a series of eliminations,
partea și mai haioasă am mai găsit un clip mai mare al aceleași sistem.
This method allows adjacent
în care apare o a treia specie de roboți, mâinile.
Here, the flying robot has already targeted the 4 robots closest to the hill.
Mâinile nu numai că puteau apuca, avea două mâini, un device respectiv, nu avea picioare, nu avea sistem de transport, veneau două de-astea rotițe și se cuplau de corpul cu mâini și îl transportau la locul faptei. Dar partea cea mai spectaculoasă care m-a dat gata a fost că în vârful tubului ăsta era puțin mai mare, deodată a făcut și sus a plecat, au aruncat cu aer comprimat un magnet care s-a lipit de tavan. Și apoi cu mânuțele s-a cățărat pe o bibliotecă și a luat din bibliotecă cartea pe care trebuia să o aleagă și pe care o găsise un zburător, o identificat într-o clădire întreagă. Și roboții ăștia mici făcuseră drumul înainte ca să arate pe unde trebuie să vină ceilalți doi cu mânuța după ei. Spectaculos. Combinație, să spunem. E drept că se mișcă încă foarte încet și cred că și aici au una dintre provocări vitele. Un alt concept care mi se pare interesant este ideea de roboți care se autoreplică. O să vă duc numai la niște linkuri. Aici e o lucrare destul de aprofundată, să spunem, asupra subiectului. Sisteme de asamblare fluide. Nu, asta nu e foarte interesant. Asta de la BBC, atunci că e mai promițător. Astfel, fiecare cărămidă de asta este o mică unitate care acționează independent de celelalte, dar care colaborează cu celelalte și care se poate, se autocopiază, ca să zic așa. Așa. Aici țin să menționez MIT, Massachusetts Institute of Technology, nu numai pentru că probabil că toți inginerii au visat să ajungă odată la MIT măcar, ci și pentru că șeful sau șefa laboratorului de acolo de domeniul media, spun ei, este o româncă. O să vă dau link-urile puțin mai târziu, dar aici am să vă arăt doar câteva dintre realizările celor de la MIT.
Our objective is to design self-assembling and self-reconfiguring robot systems. These are modular robots with the ability of changing their geometry according to task. And this is exciting because a robot designed for a single task has a fixed architecture, and that robot will perform the single task well, but it will perform poorly on a different task in a different environment. If we do not know ahead of time what the robot will have to do and when it will have to do it, it is better to consider making modular robots that can attain whatever shape is needed for the manipulation, navigation, or sensing needs of the task.
Up until now, most other modular robotic systems use servos and motors in order to have arms and attachments that move modules into different places. However, we wanted a simpler approach that uses fewer actuators, fewer moving parts, and was easier to implement on a lot of different robots. And so the approach that we chose is to use angular momentum. And essentially what that means is there's a spinning mass that spins inside of the robot. We want the robot to move, it stops that spinning mass, which takes that motion from the mass and applies it to the robot. And a part of this that's unique is that the spinning mass is completely inside the robot, and so the robot doesn't have to be in a certain position in order for the force to be acted upon the robot. And so this allows for a lot more types of motion with only one actuator.
So there were a couple challenges when we came to design the M blocks. One was fitting everything inside. So we have a relatively small volume, and we needed to fit a brushless motor controller, a flywheel, a braking mechanism, electronics, a radio, a battery. Additionally, we faced the challenge of trying to simplify and make the design as robust as possible. So we didn't want any external moving parts, we didn't want latches, we didn't want the cubes to change their shape, we just wanted simple blocks that were able to move on their own. The magnet system in the cubes is one of its key features. So we have face magnets. There's 8 face magnets that provide some coarse alignment. And then there's these edge magnets, which are free to rotate. And the key is that when a cube starts rotating, the edge magnets actually get closer to one another. So if we start from this configuration and we break the face magnets free and start rotating, the edge magnets actually get a little bit closer due to the fact that the edge is slightly cut back or chamfered. And as a result, you form a very strong bond between cubes, which allows them to stay attached as one is rotating into a new position. It continues rotating, the face magnets provide alignment, and it snaps into place.
One other benefit of having an inertial actuator is that the cubes are able to jump, and this is a capability that very few robots have, and especially very few modular robots, because in order to jump, there's a requirement for a very high amount of energy in a very short amount of time. And most robots are optimized for control, stability, and precise motion. In our robot, we found it kind of an accident that they're able to jump. We weren't intending to do that, but it ends up that we need enough momentum inside each cube in order to move on a lattice structure, which is what we intended, that we can also, when we apply as much energy as possible, it can jump through the air, which is pretty exciting because it also allows robots to jump on top of each other and to go places that they couldn't go if
o altă direcție care are legătură și cu robotica, chiar dacă nu direct, dar cu producerea de roboți și de tehnologie, este printarea 4D. Nu știu dacă am mai menționat-o și domnul Munteanu într-una dintre prezentări, dacă vă spune ceva.
This is me building a prototype for 6 hours straight. This is slave labor to my own project. This is what the DIY and maker movements really look like. And this is an analogy for today's construction and manufacturing worlds with brute force assembly techniques. And this is exactly why I started studying how to program physical materials to build themselves. But there is another world. Today, at the micro and nanoscales, there's an unprecedented revolution happening. And this is the ability to program physical and biological materials to change shape, change properties, and even compute outside of silicon-based matter. There's even a software called CAD Nano that allows us to design three-dimensional shapes like nanorobots or drug delivery systems and use DNA to self-assemble those functional structures. But if we look at the human scale, there's massive problems that aren't being addressed by those nanoscale technologies. If we look at construction and manufacturing, there's major inefficiencies, energy consumption, and excessive labor techniques. In infrastructure, let's just take one example. Take piping. In water pipes, we have fixed capacity water pipes that have fixed flow rates, except for expensive pumps and valves. We bury them in the ground. If anything changes, the environment changes, the ground moves, or demand changes, they have to start from scratch and take them out and replace them. So I'd like to propose that we can combine those two worlds, that we can combine the world of the nanoscale, programmable, adaptive materials, and the built environment. And I don't mean automated machines. I don't just mean smart machines that replace humans, but I mean programmable materials that build themselves. And that's called self-assembly, which is a process by which disordered parts build an ordered structure through only local interaction. So what do we need if we want to do this at the human scale? We need a few simple ingredients. The first ingredient is materials and geometry, and that needs to be tightly coupled with the energy source. And you can use passive energy, so heat, shaking, pneumatics, gravity, magnetics. And then you need smartly designed interactions. And those interactions allow for error correction, and they allow the shapes to go from one state to another state. So now I'm going to show you a number of projects that we've built from one-dimensional, two-dimensional, three-dimensional, and even four-dimensional systems. So in one-dimensional systems, this is a project called the self-folding proteins. And the idea is that you take the three-dimensional structure of a protein. In this case, it's the Crandon protein. You take the backbone, so no cross-linking, no environmental interactions, and you break that down into a series of components. And then you embed elastic. And when I throw this up into the air and catch it, it has the full three-dimensional structure of the protein, all of the intricacies, and this gives us a tangible model of the three-dimensional protein and how it folds, and all of the intricacies of the geometry. So we can study this as a physical, intuitive model. And we're also translating that into two-dimensional systems. So flat sheets that can self-fold into three-dimensional structures. In 3 dimensions, we did a project last year at TED Global with Autodesk and Arthur Olson, where we looked at autonomous parts, so individual parts not pre-connected that can come together on their own. And we built 500 of these glass beakers. They had different molecular structures inside and different colors that could be mixed and matched, and we gave them away to all the TEDsters. And so these became intuitive models to understand how molecular self-assembly works at the human scale. This is the polio virus. You shake it hard and it breaks apart, and then you shake it randomly and it starts to error correct and build the structure on its own. And this is demonstrating that through random energy, we can build non-random shapes. We even demonstrated that we can do this at a much larger scale. Last year at TED Long Beach, we built an installation that builds installations. The idea was, could we self-assemble furniture-scale objects? So we built a large rotating chamber, and people would come up and spin the chamber faster or slower, adding energy to the system and getting an intuitive understanding of how self-assembly works and how could we use this as a macro-scale construction or manufacturing techniques for products. So remember I said 4D. So today, for the first time, we're unveiling a new project, which is a collaboration with Stratasys, and it's called 4D printing. The idea behind 4D printing is that you take